Thank you, Vivek. Good morning, everyone. So this session is titled LLMs Unplugged, Simplifying Generative AI for mHealth Innovation. So it's a bit of a grandiose title, but suitable for the Hollywood setting of the later part of the mHTI. So what I'm going to try to do today is give you a bit of a breakdown of what the landscape looks like right now in the LLM space. So as people probably know, this is a space that's evolving very rapidly. So we're going to start with some foundations, just so you have something to hold on to a year from now when things have changed substantially. So we'll talk a little bit about AI and machine learning background. Then we'll move into large language models and generative AI in terms of how these systems work, what they seem to be capable of doing currently, a little bit about what they may be capable of doing in the future, where trends are going. And then we're going to look at use cases and challenges in mHealth in some depth. So we'll put up maybe 6 potential use cases just to get people thinking about ways that you could use these technologies. Some ways of using LLMs in the health space right now are reasonably sound. Some are a little bit risky. And so we'll talk about some of the factors that contribute to that risk. And then depending on time, we'll have some discussion. So again, as Vivek said, as questions come up, you can put them into the chat. We'll turn to questions at the end of the presentation. All right, so to get started, just again, to level set sort of in AI and machine learning, what is AI? So this obviously over the last maybe 5 years, artificial intelligence has really sort of emerged as a consumer technology. So prior to that, there weren't really consumer-facing applications of artificial intelligence that many people were interacting with. That's no longer the case, thanks to tools like ChatGPT and lots of other emerging sort of AI systems that lots of people have access to. That said, there's still a lot of misconception about what artificial intelligence actually is as a research field and sort of what it comprises. There's some conflation of sort of what machine learning is with what AI is. So what is AI to start? So as a research discipline, it encompasses a number of different specific areas. Knowledge representation is one. So how do we think about representing what we know? How do we think about distilling data into different forms? Another sub area is reasoning. So once we have some information, how do we think about drawing conclusions? Reasoning can be logical, it can be probabilistic, there are different forms, but it's its own separate task. It encompasses problems like planning. So given information, how do we think about a series of steps to accomplish some particular goal? Perception is another aspect of artificial intelligence that's about reasoning based on sensor data. So if we have data from vision systems or wearable sensors, other kinds of IoT or infrastructural sensors, how do we think about taking those perceptions of the world and mapping them into different kinds of decisions, actions, or insights? Planning, as I mentioned, is sort of synonymous with reasoning, sort of builds on top of reasoning as a kind of task that you might like to perform that, again, exhibits multiple facets of intelligence. So we interact with planning regularly using tools like GPS. If we ask Google how to get from point A to point B, it comes up with a plan that takes into account the road network and traffic conditions and things like that, that you can then execute sort of step by step. And there are lots of different instances of planning within AI. Another area in AI that ties into LLMs is a problem of synthesis. So not just how do we reason based on information that we have or try to perceive the world, but how do we think about generating things that are new? So fundamentally, when we're thinking about LLMs and generative AI, a lot of the sort of aspects of that capability are about generating new things, right? So synthesis based on existing information. And the last component that we'll talk about in some more detail is learning. So how do we think about building systems that are adaptive, that can take in information and change their behavior over time in response, right? So again, there's lots of separate work on all of these pieces. One of the interesting aspects of AI over the last maybe 15 years or so is that learning has really come to be fundamental for the other subdisciplines of AI. So there are approaches where you learn to reason, you learn to plan, you learn how to perceive, you learn how to generate. So machine learning is sort of the core of a lot of these different capabilities at this point. So again, machine learning maybe has a 50 or 60 year history as an independent discipline. A definition going back to sort of the late 1990s is the following. We would say that a computer program is said to learn from data D with respect to some class of tasks T and performance measure P if its performance on these tasks as measured by a performance metric, improves with access to data. Right? So this is the basic idea that we are going to attempt to learn to do something, right? Not just learn in general, but learn with respect to some specific task. And that the way we're going to learn is to have access to some form of data. Right? So there are multiple different forms of machine learning that are based on access to different kinds of information. So this definition, again, goes back to Tom Mitchell, a researcher at CMU, from his book in 1997. So we're going to drill down a little bit further. In this broad space of machine learning, there are different forms of learning. The form that is most relevant for LLMs is something called supervised learning. So in supervised learning, what we're trying to do is correctly predict an output that corresponds to a given input, and we're going to try to learn this from input-output examples, right? So in machine learning, this is one of the most common forms of learning. And again, you'll often see this conflation that I talked about where people think about supervised learning as being the only kind of learning, or think about supervised learning as being all of AI. Clearly, there's more going on than that. But this is the relevant form of machine learning for the topic of LLMs that we're going to focus on today. So there are lots of different examples of supervised learning in the literature and in common practice. An example of this framework would be something like image recognition. The basic task that we're interested in performing is taking an image and then saying what the object is in the image. So in a classification task like this, we maybe have some pre-existing set of classes like cars and cats and dogs and airplanes that we're interested in categorizing images into. So the input is the image, the output is the label. So what type of object are we looking at? A more mHealth flavored example would be something like cigarette puff detection from wearables. So maybe we have respiration data, and we're looking at categorizing respiration cycles in terms of whether they correspond to cigarette smoking puffs or not, right? So again, here our inputs are these waveforms coming from the sensor, and the output are the labels. So I want to go into a little bit of detail around how supervised learning works and what the components are, because these are the components that large language models are built out of. So we'll look at this in a little bit of abstraction, and we'll drill down to what it looks like to build a language model specifically within this kind of framework. Okay, so the basic problem that we're interested in supervised learning always is a prediction problem where we have these inputs and we're trying to predict some outputs. So it sits in the middle of this is a structure that we refer to as a model. The model behaves like a mathematical function. You can think of it as taking an input that we'll call x. The model processes the input and produces an output. So in the smoking puff detection case, we take our waveform, we run it through the model produces an output. That output, let's say, is a label for smoking, not smoking. So maybe this example corresponds to smoking. A really important facet of the way machine learning works is that these models depend on a set of parameters. So here we're using the Greek letter theta to indicate that parameter set. And you can just think about the parameters as being a set of knobs or sliders. They're real valued. You can change the value of them. And as you do that, what happens is you change the relationship between inputs and outputs. That's the basic structure of these models. So the model has some mathematical function that it implements, but it depends on this auxiliary set of parameters. The way we get access to different specific functions is to set the parameters of the model to different values. Okay? And again, the task we're trying to perform here is this prediction task. When we're looking at applying models like this, especially in the healthcare setting, often we don't actually want the most likely predictions. If we're trying to do something like assess risk, it can be more useful to have access to probabilistic predictions. So instead of just saying, we think this example corresponds to a smoking puff, instead it might be more useful to say, we think this example is not smoking with probability maybe 0.45 and is smoking with probability 0.55, something like that. Okay, so we have a probability distribution over the potential labels of the input instead of just making a hard prediction for what we think is most likely. And this is in fact how these models are learned. So they're learned based on predicting probabilities and then looking at how those probabilities correspond to true labels. So in order to use these models for learning, we need examples of inputs and we need examples of outputs that we'll call the labels. And then we need some way of comparing them. So for folks from the CS or stats side, the typical way to do this is with standard maximum likelihood learning. For folks that aren't familiar with those terms, all we're doing is comparing the probabilities that we generated to the true labels, we're looking at the probability of the true label as the sort of signal that we use to learn the models. What we'd like to do is make the probability of the true labels as large as possible. That's the basic likelihood principle. So we use a structure called the loss more generally to perform that comparison. There, in that particular framing, we're trying to minimize the loss that the labels have under this distribution. And then based on that loss, we can decide or sort of derive a rule for how to update the parameters to improve the loss. So maybe we have some change to the parameters, we feed it back into the model, the parameters change to try to make the correct label, in this case, more likely. Right? So relative to what we had, maybe we see this particular example, we update the model, we change the parameters, and now this specific instance becomes more likely to be smoking than not smoking, given that smoking is the correct label. Okay, so that's the oops, sorry.
Shane, can you check? Oh, there you are, Ben.
Yeah, you guys can hear me okay? Sorry, yeah. Teams just dropped me out. Microsoft didn't want me giving away the secret sauce here. Hold on a second, I'll reshare. We'll pick it back up again. Okay, there we go. All right, can you guys see the slides again?
Yeah.
Yes.
Good. Okay. All right. Hopefully our connection will hold on here. All right. So as I was saying, this is the basic structure for how we represent models and how we learn them from data. Right. So a couple of additional notes here. When we're thinking about building models like this, the example that I showed was just using one input-output pair and was updating the model to try to do a better job on that example. In reality, when we go to learn these models, we need lots and lots of examples. When we think about organizing that data, the collection of input-output examples that we use to train the model is referred to as the training data set. Importantly, when we go to perform evaluation, we need to use new data. So you don't want to look at how well your model performs on the data that you use to train it. You want to look at its performance in a separate set, and that's called the test set. And this is actually a challenge for LLMs that we'll come back to later on. The commercial LLMs train on all kinds of text data that they can find all over the place. Coming up with new things they haven't seen to actually evaluate them on, or even knowing what they've been trained on, can be a little bit challenging. In the more traditional supervised setting, things are a little bit more controlled. So when you're using a model someone else has built, this evaluation problem can become a bit of an issue. The other thing I'll note here is about model capacity. This is also relevant to the L in LLMs. So the L stands for large. What does that mean exactly? We generally think about the size of models in terms of their parameter count. So how many parameters are in the model? How many knobs are there that we can adjust to change the behavior of the model? Generally, models that are larger, that have more parameters, are more flexible. That means they can model more complex predictive relationships, input-output relationships. But all the model architectures that we know about basically require more training data to learn larger models. So this is sort of a related to something called the bias variance trade-off. You can either have models that you can train on less data, but they're more restrictive, less flexible, lower capacity, or you can have models that are very flexible, but then it requires lots of data to train them and come up with something that's actually performant. So in traditional machine learning, we're always looking for a trade-off between the model capacity, how many parameters it has, and the amount of data that we have to try to build something that makes effective predictions. LLMs sort of shift that a little bit, again, by training on very huge volumes of data and enabling the use of very large models. And we'll look at how large the models are and how much data they're trained on in a little bit. Okay. All right, so that was a rapid overview, just to level set on machine learning and AI in general. What we're going to do for this part of the presentation is just dive into LLMs, how they're structured, what their parameters look like, what kinds of data they're trained on, and then what they can do after they've been trained. And I think really one of the more interesting aspects of these models is that they somewhat violate Mitchell's notion of what it means to train a model to perform a particular task. So they are trained to perform a specific task, but I think all of the excitement about them has to do with the emergent capabilities that they appear to have, even though they've only been trained to perform one kind of task. And so we'll talk about some of those capabilities that emerge via the way these models are trained. Okay, so to start, we're going to talk about what a language model is, then we'll talk about what a large language model is. Language models are not a new kind of idea. The work on language models goes back to 1913, in fact, work by Andrei Markov looking at character-level language models. The definition for a language model is that it is a probabilistic supervised machine learning model of the kind that we just talked about. They accept natural language text as input, and they predict a probability distribution over the next item in a sequence, which is either a character, something called a token, or a word. We'll talk about what a token is in a second, as the output. So that's the basic predictive structure. So the task the models are trained on is next word prediction, next character prediction, next token prediction. And again, they take as input a representation of text, right? So this falls squarely into the supervised probabilistic model definition that we just looked at. It's just a specific kind of task. So instead of taking waveforms for respiration and predicting puff labels, or taking images and predicting object classes, we're taking a natural language prefix for a sentence, let's say, and predicting what should come next. And so just a specific example of a type of task that falls under the supervised heading. So this idea of the level of the language model is a little bit interesting. So you can build these models in different kinds of representation spaces. So you can build a language model at the character level. So what that means is we're using like the letters of the alphabet, maybe we're using different punctuation numbers and things like that as the base representation. So there may be like a few hundred different characters that we would consider if we're looking at plain text. If you're looking at Unicode and you have emojis and things like that, it gets a little bit more extensive. But if we're looking at just regular letters, numbers, and punctuation marks, there's maybe on the order of 100 different kinds of characters that you would need to represent. But then your encoding of text becomes very long, right? You're representing every individual character as a separate symbol that you then need to process over. So that tends to generate very long sequences, and it's not particularly efficient for current models where you're trying to process entire documents, for example, or collections of documents. The opposite end of the spectrum is to build language models on top of word representations. So this is the trade-off where now the text encoding becomes much shorter because you're thinking about words as being the sort of primary thing that you're representing. But then the vocabulary size is much larger. So there's maybe 1 million plus words that you might need to represent. That's assuming things like correct spelling. When you start looking at inclusion of proper nouns, so names of people and other entities, it gets even larger. So the representation directly using words is inefficient for a different reason, and that the vocabulary size, the number of different possible values that your predictions can take, becomes very, very large, right? So language models, in particular LLMs, use a notion called tokens as the fundamental representation for the text data. A token is sort of in between, it's in between a word level representation and a character level representation. Different models use different tokenizations. They break up the words in different ways. So here, this example is from the title of the talk. So you can see it broke LLM up into L and then LM and S separately. These representations tend to do things like split off prefixes and suffixes. They represent most base words on their own, and so on. So it also split up sort of mHealth into mHealth because that's not a word that exists in the sort of basic word level vocabulary. So this gives you a flexible trade-off where you can sort of represent basically anything, any surface form using some set of tokens. And again, there's typically something like 100,000 different tokens in the token representation. And this gives you sort of medium length text descriptions, right? Text representations. So there's different trade-offs here. Early work in language models used character representations. There's work through the 80s, 90s, and early 2000s using word level representations. LLMs basically adopted this token representation to get around the problem of needing very large vocabularies for dealing with proper nouns and other kinds of strange surface forms in real text that you might find on the web. So lots of models today are using tokens. If you look at how you're charged for using an LLM, you're charged based on how many input tokens you generate. or how many input tokens go into your prompts and how many output tokens come out. So just keep that in mind. The tokens are not words. When people describe language models, they typically do it using words as a sort of analogy. So although these models don't actually use words as the representation, it's reasonable to think about them in that way. We'll do that for most of the talk. It's important to recognize that this distinction exists. Okay, so in terms of the way models work, the modeling is sort of agnostic to what the representation is. We can think about a sequence of inputs. Those inputs are either characters or tokens or words. The basic structure of the model is the same. So we'll have an input. In this case, basic example, we prompt the model with an input that says the capital of France is. The prediction task is to predict what word we think is going to come out next. That prediction is in the form of a probability distribution over the vocabulary. So in this case, for a word level model, we're looking at maybe all the words in the dictionary. So, running through that set of items, we come on the words pairing, Paris, parish, parasite, and so on. What we would like here is for the probability of Paris to be higher than the probability of all the other words, because that's the correct answer. But again, recognize that what we have is a probability distribution over whatever the output space is. And if we had tokens, we wouldn't be predicting the next word, we'd be predicting the next token. Paris might be a token in that vocabulary, it might not, depending on how the space has been tokenized. Right? So once we have this in terms of generation, there's one additional step, which is what exactly do we pick? So again, in a more normal supervised setting, we would usually always pick the most likely output and predict that. In LLMs, things are a little bit more flexible because the output space is so large. Often there might be multiple words that are synonyms of each other, and it really doesn't matter which one we pick, and maybe you want to get more diversity in the generations that you're producing. So there are different kinds of rules. So something like maybe pick uniformly amongst the top K words, the top K words with the highest probability. Something like that, right? So there are different kinds of specific approaches you can use to pick a representative out of this distribution that's not just the most likely. Predicting the most likely is often referred to as greedy decoding. So here, if we apply greedy decoding, we just get the word Paris out as the prediction, but there are other kinds of strategies that you could use. And in current LLMs, some of that flexibility is exposed to you. So in ChatGPT, you can do things like control how smooth or sharp this probability distribution is, how many words are considered in the top K list, and so on. So current LLMs do expose some of this sort of architecture of the decoder to you to give you the ability to generate in a way that's a little more flexible. Right? So everything that's in this gray box is what's considered to be the language model. So it's the model structure, the model architecture itself, the settings of the parameters, and whatever the structure is for the decoder that's being used. Right. Okay, so that's the basic prediction task. Sentence goes in, some representation of the sentence goes in, a character or a token or a word comes out the other side, right? And so this is a sort of one-shot generation. We've generated one item based on the application of the model, right? So if we want to generate sequences, which is what we're typically doing with LLMs, again, we can do this with any language model. The models are basically applied recursively. So in this example, we start off with an input once upon, we run it through the LLM box that we just described. Maybe the LLM decodes and chooses as the next symbol. So we get once upon we take the A that comes out, we can concatenate it with the original input. Now we have once upon as our input, and we feed it back through the language model. So maybe now the LLM outputs time as the output. We can concatenate it back again. Now we have once upon a time. We're starting sort of a children's story or something like that, bedtime story. And then we feed that back into the language model, generate our next token. So that basic block of taking an input and generating a single next output extends into outputting arbitrarily long sequences by taking the generated outputs, concatenating them with the previous input, and running it back through the language model. Right? So these models typically have a special word or token or character that indicates the end of generation. And when that token is generated, when that symbol is generated, then the generative process stops. Right? So it needs some way to generate a stop symbol so that it knows when to end the generation process. Right? So that's the basic structure for how these language models can be used to generate arbitrarily long sequences. And again, if you've interacted with something like ChatGPT, you see it generating output sequentially not a character at a time, but usually a word at a time as it runs. And again, this is what that process looks like under the hood. The reason why it takes some time and it's generating sequentially is it's running this process of taking its own outputs, putting them back into the input and running them back through the model to make a subsequent generation, right? So you do have this ability to sort of stop the generation process along the way if you can see that it's already sort of off the track relative to what you were interested in generating for longer generated outputs. So this is the basic sequential generation process. In terms of how these models are trained, just to give some sense of what's going on, again, the task is just this next word or next token prediction problem. So the training process looks exactly the same as it did previously for our puff detection example. You produce a probability distribution over outputs. You have a correct output, again, the label. So again, based on the natural language text that you start from, you know what the next word is. And you just combine these two again. You run them through your loss, and you update the model parameters. Right? So it's exactly the same learning process that we saw previously. So a single, paragraph of text generates many, many examples by sliding what you're considering to be the next word that you're predicting along that chunk of text, right? So a single document generates many, many examples where every word effectively is being used as the word to predict, or every token is being used as the one that you're trying to predict based on everything up to that point. Okay, so again, the basic idea here is the same as for basic supervised learning. We need a data set to train the model. Our models will have some number of parameters. Everything that I mentioned previously holds in that the larger the models are, the more data we're going to need to train them. And so we'll talk about where that training data comes from for LLMs. Before we do that, I'll say a couple of things about language models. So I mentioned that language models are not a new area. They've existed for a long time. Again, the work going back to 1913 used a specific form for the language model function. So the piece that sits in the middle here, what is it? It could be lots of different things. So these older models, original models, use something called the Markov chain at the character level. They really just looked at what is the probability of the next character given what the current character is. So you can sort of visualize that as a chain. As you move through that chain, you're always just looking at what is the current character and then what's the probability of the next character. So they have a quadratic number of parameters in the size of the vocabulary. That means sort of of 100, sort of 100 squared parameters if we're talking about applying this with maybe something like standard ASCII characters. Through the beginning of the 1980s and subsequently, this basic idea of the Markov chain, looking at one character given a previous character, was generalized to structures that can sort of hold on to representations that are more flexible as you move through a sequence. So these models are called recurrent neural networks. They have a number of challenges when you try to apply them to very long sequences. So we won't say in detail what these models are doing, but the main takeaway here is the longer the sequences are, the harder it is to learn the models, the harder it is to get them to hold on to useful information that you can use to make different kinds of predictions as you move through the models. So these models were sort of the state of the art, let's say, in language modeling up until about 2017 or so, where a new architecture was introduced called the transformer architecture. So the T in ChatGPT stands for transformer. GPT stands for generatively pre-trained transformer. We'll talk about generative pre-training in a second. Again, I'm not going to go into the architecture details here. These models have an advantage at a high level that has to do with parallelism and computation. So they don't need to process a sequence one position at a time. They can process all the sequence elements simultaneously. And so on current compute hardware, that gives you a large advantage when you're trying to train models. They both are able to exchange information backwards and forwards across long sequences very efficiently at a sort of information flow level compared to the recurrent neural network. And then simultaneously, that exchange of information backwards and forwards across long sequences is something that is sort of an inherently parallelizable computation. The other ingredient in the rise of these models is the use of what's called a graphics processing unit, or GPU, to do the compute. And so you may have heard in the news stories over the last couple of years where Facebook had noted that they would acquire a certain number of GPUs. I think they have like 100,000 or something like that recently from NVIDIA, which is one of the main providers of GPUs. And again, you may have heard lots of talk about NVIDIA and its stock price over the last couple of years as we've seen the uptick in LLMs, as they're one of the primary providers of the hardware that's used to actually run these models. right? So we won't go into more detail about the specific architecture. Again, this came out of a research group at Google in 2017, and subsequently is the foundation of all of the large language models that currently exist. Undoubtedly, this architecture will change over time and may be supplanted by something else. The basic structure of the language model won't change because it's tied to the task, right? So you still need to have a similar kind of input-output behavior. What sits inside that model box is something, again, that can change. And hopefully, we'll come up with architectures that are even more efficient than the transformer. And we'll talk about energy use a little bit towards the end, which is one of the sort of major drawbacks for these models. Okay. So in terms of the L in LLMs, the largeness, right? So we mentioned off the top for supervised learning that we think about models in terms of their parameter count when we're looking at how large and flexible they are. So this table just runs through some of the models, again, that you may have heard of or interacted with. So ChatGPT from OpenAI has been backed by a sequence of different models, GPT 3 and 4. There are precursor models that are smaller. The parameter count here is listed in billions for these models. The current model that sits behind ChatGPT is a version of the GPT-4 model. OpenAI stopped disclosing exactly what their models are doing between GPT-3 and GPT-4, so we don't exactly know. I think it's sort of expected that the model has somewhere between 500 billion and 1 trillion model parameters. There are other sort of lots of other participants in this marketplace. So Facebook has their own set of models. One of the interesting things about the Facebook or Meta models is that they're released in what's called open weights form. So you can actually download the model and run it locally if you have the resources to do that. So there's a little bit more transparency about what or much more transparency about how the models from Meta actually work. And there are many other entities that are in this space of coming up with models. Training these models is very expensive because the models are quite large, and the amount of data used to train them is also large. So the number of training tokens is represented on the far right column. So you can get some sense of how much data are going into these models. And again, this is in billions of tokens. So the GPT-4 model underlying the current ChatGPT was trained on about 1.3 trillion tokens of data. The Llama models have been trained on even more data, up to sort of 15 trillion tokens of data. So very, very large scale training data to learn these models with very, very large numbers of parameters, right? So again, you can run on sort of reasonably priced hardware. You can run some of these models like the Llama 3.3 70B locally on your own hardware with 70 billion parameters. Something like that is feasible. The larger models at 400, 500 plus billion parameters are quite cumbersome to try to use locally. We'll talk about why that might be relevant a little bit later. But again, up to sort of currently, so up to something the size 70 billion parameters, there is some possibility that you could run that in your own sort of local compute infrastructure. Okay, so in terms of training data sources, again, we might expect something like 2 to 3 tokens per word or something like that on average. So the number of words of data that are being used to train these models is just gigantic. Meta and OpenAI and the different players in this space have basically accumulated data sets of all open data. So things like open books, science papers, so research articles that are available on the web, legal documents, patents. The data sets typically include a common crawl of the entire web, all of Wikipedia, Reddit posts. Interesting capability of the models currently is around code generation. They're doing things like consuming all open source code. So the models can learn how to generate code, which is interesting. They're consuming that kind of information. Other specific websites like Stack Overflow, other question answering websites, other kinds of chat logs, basically whatever you can sort of get your hands on and download from the web is likely in use to train these models. Early iterations very likely or are sort of likely to contain different kinds of copyrighted information. We'll talk about sort of what litigation looks like in this space because entities like the New York Times think that their proprietary data has been pulled in through things like the common crawl. There's open lawsuits to try to resolve the licensing of that information. Okay, so let's train data sources quickly. The next thing I want to talk about is sort of how the models actually get into a shape where you can use them. So how do you actually get to something like ChatGPT from something like applying the training procedure that we were looking at back here to this huge collection of data that you downloaded from the web and found from different places, right? So this base task is just to predict the next word or the next token. When you build a model that does that, what you have is sort of a raw LLM. This is where the generative pre-training piece comes into the term GPT. So this next token prediction task or next word prediction task is referred to as generative pre-training. Once that's accomplished, you have a model where you can prompt it in this example. You give a text fragment and the model will continue to generate. The models are not trained just in that way, are not particularly good at instruction following. So again, for folks who've interacted with ChatGPT, you know you can give it a prompt and ask it to do something or tell you something or answer a question, and it will do that. That style of prompt is not exactly what the models learn to do when you train them in this way on arbitrary text. They're able to continue generating from a text prefix, matching style and language and things like that of the prefix, but they're not particularly good at following instructions, and they have no sort of safety considerations built into them. So this sort of next layer of training, that's often called post-training or alignment, is designed to try to get the models that have all this sort of information from the training data distilled into them and ability to generate text to get them to actually behave in a way that is helpful. So there's a step called supervised fine-tuning or SFT where you generate or you can generate sort of human written prompt response pairs. And the idea is to get the model to do better at following instructions or performing specific tasks. So if you show the model some examples of what it looks like for someone to ask a question and then provide a response, that kind of interaction is not what most of the training data actually looks like. So the models require additional training to actually provide that capability. You can also use supervised fine-tuning if you have your own data to get the model to perform a specific task. So if you were interested in a task like sentiment analysis, or you're interested in, let's say, coding survey responses with respect to a set of codes that you define. If you have some examples, you can take a raw LLM and train it to perform that specific task, and it will use its generative pre-training and whatever domain knowledge it's distilled from its training data as a basis for performing that task. So this is often called transfer learning. You've trained the model on one task, you have another task you're interested in. With a small amount of data for your task, you can fine-tune the model on that task, and often that performs quite well. So it was one of the early demonstrations of this transformer architecture sort of capability. It performs very well under task-to-task generalization via this fine-tuning process. There's another kind of post-training called preference optimization. So people, again, may have heard about something called reinforcement learning from human feedback, which is one example of this. Here, the idea is that you have the model generate a response, set of responses based on a prompt that you supply, and you have human annotators assess the different outputs that were generated and select which ones are better or rank them based on a set of criteria. And so here, often the criteria have to do with truthfulness, helpfulness, and so on, where, again, assessments are made, and then the models are updated to try to promote the generation of examples that annotators find more truthful or more helpful, or whatever the criteria are that are used to drive the ranking. So when you interact with ChatGPT, you're not interacting with a raw LLM. You're interacting with an LLM that has undergone supervised fine-tuning to behave like a helpful assistant, as well as this kind of preference optimization to generate outputs that human annotators found to be preferable to other generations. Okay. Once that's done, the additional layer that you have access to as a user of these systems is really about prompt engineering. And again, I'm sure everyone has heard about prompt engineering. The basic idea is when you go to prompt one of these models that has been post-trained using supervised fine-tuning and preference optimization, you can construct your prompt in different ways, and you'll get different performance out of the system. So there are some strategies that are currently quite commonly used. RAG is retrieval augmented generation, the idea that maybe you have a collection of documents that's relevant to answer a particular question. Maybe you can go to the internet, do a query, get a bunch of web pages, or retrieve a set of other documents. You condition on the content of those documents as part of the prompt or the input when you generate an answer. That tends to improve performance on a number of different tasks. Another kind of prompt engineering strategy is something called COT or COT, which stands for chain of thought. And there, the strategy is to try to break down more complex scenarios or complex prompts into a sequence of steps. You can do this explicitly with existing LLMs. ChatGPT does some of this internally. This is one of the major things that the DeepSeek model that came out earlier this year was doing. So what I refer to as reasoning models are models that try to enforce their own chain of thought process and break down responding to a query via a sequence of steps, where they look at intermediate goals sort of along the way. Right? So there's a lot that you can do at the prompt engineering level once you have access to one of these models to try to get it to give better performance for a particular task. Again, the two kinds of things you can do are the supervised fine-tuning using data from your own task or prompt engineering in terms of methods to apply on top of their models that come out of this post-training and alignment phase. Right? So there's quite a lot of interesting techniques that can be used there. So we'll do a capabilities breakdown and we'll move on to what this looks like in mHealth in particular. So the basic capability set that's claimed for these models following post-training is that, like generally, so for models like ChatGPT and for Llama 3.3, they're able to follow instructions given in the input quite well. So they'll generally try to do whatever it was that you asked them to do in the prompt. They're able to generate fluent text in different styles and formats and languages, including computer code. So most of the models at this point are multi-language. They're not just trained on English, they're trained on text from lots of different languages. They're able to do things like translate between languages to some degree as well. So again, when you give an input prompt in English and you ask to generate computer code, that's another kind of translation from sort of English to code that these models are quite capable of performing as well. The training process distills knowledge from the data set into the model parameters. And again, these models are able to recall information and answer questions about that information that's been distilled. We'll talk about sort of issues a little bit later on. None of these things are exactly perfect. If you look at the ratio of number of model parameters to amount of training data, there's quite a compression process that's going on. So it's entirely possible that certain kinds of facts are sort of stored in the model in a way that's incorrect, or that when they're recalled incorrectly. So that's often called the hallucination problem, which is an open problem with these models. They don't always produce factual information, and sometimes the errors can be quite egregious. These models are able to semantically manipulate text data quite well. So summarization is a really nice application for these models. Currently, you give a piece of text or a larger document and ask for a summarization of it. These models are able to do that quite well. Another capability for these models is something called in-context learning. Here, the idea is that the models are able to generalize from a few examples given in the prompt to solve a novel instance of a problem. So in general, for supervised learning, you would have to have a large data set in order to solve a problem. You give lots of input-output examples. LLMs tend to be able to see a few different examples of tasks that they're maybe familiar with, and then recognize what that task is and provide outputs for novel inputs. So again, that's leveraging sort of the domain knowledge that the models have distilled out of the training data. So this is another prompt strategy where you can describe a task you'd like to solve. You can give some input-output examples of how the task is supposed to work, and then you can give some novel inputs and hope to get higher quality outputs back than if you hadn't used that particular strategy. And so again, it's another useful tool in the prompting toolkit. Just a couple of examples. Again, I'm sure people have seen these kinds of things, but the summarization, again, for paragraph level text into a sentence level. So this one's just asking ChatGPT to summarize a little paragraph here into 10 words. It pulls out the general themes. Again, you can take document level input, so an entire PDF, upload it, and ask for a summary back into a paragraph. The models are quite good at doing that. Some of this functionality is integrated into tools like Zoom, where you can take your Zoom transcript for a meeting, turn it into text using speech to text, and then summarize that in terms of meeting notes or to-dos. We're seeing these kinds of applications sort of coming into routine use in business pretty rapidly. It's much more, well, again, you have the hallucination problem in terms of details being synthesized that weren't present. You have to be a little bit careful with verification. But this kind of application seems to work quite well. Code generation is another example. Give a text prompt for the generation of a piece of code. This was asking to generate a regression model, code to apply a regression model to an uploaded file. These models are able to do things like that. Routine coding tasks, different kinds of boilerplate that's typically needed for things like developing apps. These models are able to do that pretty effectively, and it's because they've been trained on huge amounts of open source code. So their ability to support software engineering tasks that are routine is quite good. Their ability to do novel programming tasks is maybe a little bit more or under development, let's say. Okay, again, this is an example of in-context learning, giving a few examples of product reviews and ratings, and then asking the model to complete one. It's able to do that quite well. And again, this prompt didn't include a description of what the task is. It didn't say we're talking about product reviews and ratings. Just asked to complete the last example and gave a few examples. So the last example here is this is a terrible product, didn't work out of the box, and the instructions were confusing. And ChatGPT comes up with the idea that that should be associated with a rating of 1, right? Just based on the 4 examples that are here. So this shows that recognition of the model, what task is it trying to perform, what task were we trying to perform, and then generating an appropriate output for a novel input that has no output associated with it. Again, this, lots of applications of this kind where you can potentially provide relatively small amounts of in-context training data and have the model sort of impute what supervised task you're trying to solve, and then solve it for novel instances. Okay. In terms of other kinds of extensions, so the title for the talk was Gen AI, right? So what else exists in generative AI? We've been talking about LLMs. Fundamentally, LLMs are doing next word prediction, so they're able to generate natural language and things like code. But what other kinds of things can we do, right? So there are some specific extensions of LLMs to more sort of specific products. So one example is the application of LLMs for something that looks like a research assistant. So again, people may have seen a system called Notebook LM. It's a demo system from Google. It's quite interesting. I encourage people to check it out. You can drop multiple sources into it, so PDFs or other kinds of documents. And it supports question answering against that set of documents. So you can ask questions, you can ask for summaries, and it will go through and sort of run natural language understanding via the LM and generate responses. This particular product, Notebook LM, can also generate audio summaries. It will generate a podcast-style digest of a collection of sources for you, about 15 minutes long, that you can listen to as a summary instead of reading through all of the documents. Right? So that's an interesting set of sort of immersion capabilities there. I already mentioned code generation. There are more specific tools for doing code generation. There's a platform called Cursor, which has become popular over the last little while, that will edit large code bases. It's sort of falls under a newer category of models called agentic models that don't just generate code. They can use tools like web search or call different kinds of APIs. So Cursor can edit code, it can commit code to Git or version control, if you know what that is. Can take your code and post it to your website and things like that, depending on what your specific application is. So this goes beyond just generation to models that are performing tasks in the real world via access to the web in different ways. But those are all still sort of fundamentally manipulating text in different ways. Another part of the space that's quite interesting is multimodal generative AI. And again, I'm sure lots of people have heard about these applications as well. So this includes things like image to text. So you take an image and ask for the generation of a text description or support for tasks like visual question answering. So I'm pointing out some commercially available versions of this. So you can do this with ChatGPT 4 Pro or Gemini 1.5 Pro from Google. Upload images and ask questions about them or get different kinds of descriptions. You can do the reverse. You can do text to image. So you can generate and edit images based on text prompts. So again, OpenAI, this model is called DALL-E 3. It's integrated with ChatGPT 4. Adobe has their own product here called Firefly. Text to video is still sort of in progress to a greater degree. But it's the same idea. You generate video based on text prompts. OpenAI has a model called Sora that can do that. There are a number of other sort of academic and sort of early stage models. I believe Sora is the only one that's available now. There may be some others that can do video from text. And again, this is all relevant for different applications in mHealth, as we'll get to in a second. So I'll just show one example of something fun here for text to video. So the prompt here is, Rockefeller Center is overrun by golden retrievers. Everywhere you look, there are golden retrievers. It's a nighttime winter wonderland in New York City. There's a Christmas tree, et cetera, et cetera. So let me just run it again. So at first glance, this is pretty convincing. If you look at it very carefully, you can see there are a number of sort of odd errors in the generation. But at a top level, for short clips like this, where you don't need something that's too accurate, these models are working quite well. So for like, background footage or something like that, for video content, these models will be quite reasonable shortly. And again, that's why Adobe, for example, is interested in this space quite heavily. Okay, so that was sort of a whirlwind tour of what these models are currently doing. I'm going to go through and just point out some use cases and challenges in mHealth to wrap up. So to start, these models are quite good at things like translation. English to English translation is something that they can do. And so a useful sort of application for these models in mHealth is potentially the translation of complex medical and technical language into plainer language. So this has the potential to do things like improve comprehension of consent documents when you're looking at putting together IRBs, study protocol instructions, and other kinds of documentation. So there's well-defined notions of different levels of health literacy, the ability to target for those levels using these kinds of English to English translations, if you will, is something that these models are able to do now. So you would still want a verification process where you plug in with a prompt what you're looking for and then verify and potentially further edit the output to ensure that it's correct and hasn't dropped any important details. But that's a sort of ready-to-go application for this technology currently. Another ready-to-go application is around user simulation. So LLMs can be prompted to respond according to a description of a persona. If you already have personas developed to support the design process, and again, you may have heard about this already from Pension Cluster or others in mHTI, if you have these personas developed, you can drop them into an LLM and provide some level of simulation of users or study participants who sort of respond based on what those persona descriptions are. You might be able to get some relevant feedback that you can use to tweak designs before involving real participants. This is not a substitution for having real participants in a user study, but is an intermediate step that previously wouldn't have been possible. You would sort of develop a persona and think about it, reason about it, use the persona. Here you have the ability to potentially actualize the persona in a simulation, which again may expose considerations that you hadn't thought of previously. Another ready-to-go application is intervention content generation. So if you're looking at things like text or image-based or even potentially video-based content, using text prompts to generate variations on your message bank, if you're doing some form of adaptive intervention tailored to different kinds of contexts, is something you can definitely do with these models. Again, you want to do that in a generate and verify kind of mode. And there's also the potential to condition this generation process on relevant behavioral theory. So if you're building an intervention and you're using some specific underlying theory, you can drop that in as context and try to generate intervention content that is both consistent with your tailoring and whatever your underlying behavioral theory looks like. And again, it's basically ready to go as an application. Analyzing participant free text as something else that's potentially helpful. So if you're doing things like qualitative coding, first cut at that using LLMs is something that's definitely possible. They're able to categorize text for facets like sentiment. Again, using methods like in-context learning, you should be able to prompt these models to give you helpful interpretations of the text data that you have. If you're looking at studies with large volumes of free text, this is something that's potentially helpful to do. Again, still relies on someone looking at those assessments, not sort of an end-to-end application. So this is still sort of a generate or reason and verify kind of application of the approaches. We talked a little bit about automating programming tasks. So for simple things, this works now. You can use ChatGPT. There are other kinds of models like Claude Code that you can use. This application I mentioned, Cursor, will generate entire code bases for you. Probably not a good idea to generate your mHealth app using Cursor currently, but it might be able to generate components of applications or help with edits to larger code bases, specifically around routine tasks like implementing user interface components based on specifications or sort of Figma sort of mock-ups. So it's sort of emerging. The one that I'll put a sort of caution on here is the personalized health coach involving intervention participants directly interacting with a large language model. There's lots of different forms of this that you could think about looking at wearable data and other forms of data. The potential for models to hallucinate and generate inappropriate or erroneous responses is still not trivial with these models. So there's some risk involved in putting a model, where a user has free interaction, free chat interaction with that model in front of someone in the context of a health study. So content generation with review is reasonably sound. Doing this, there are people that are using this kind of approach. Just note that there is risk to doing this. There are multiple instances of models sort of going off the rails under prolonged chat interaction with users with fairly significant consequences. Okay, so we'll talk about sort of why that happens. Again, this hallucinations and inaccuracies problem really is sort of an unsolved problem with these models coming to challenges. Information that is distilled out of the training data isn't necessarily done so in a way that's completely correct, or it's not always correctly retrieved. When you ask models to make recommendations or reason over inputs from users, they can do a variety of things that are sort of inappropriate. There's some examples from the last year. This is from end of last summer. When Google introduced AI summaries at the top of its search results, there are some pretty strange things that were generated in that first couple of weeks. There was one set of recommendations where the model was telling users to eat rocks to improve their vitamin and mineral consumption. There were several other sort of strange examples that came out from that particular application. So in lots of cases it was correct, but there were corner cases where it was doing strange things in response to routine queries, right? So this is an odd one related to hallucinations. There are many other examples. I mentioned active litigation already. So, I mean, there's an open court case that I mentioned by the New York Times against OpenAI. There are other cases against OpenAI with respect to image generation in terms of the sources that they're using. So their image models generate output, clearly using copyrighted characters and things like that. So how that will be resolved is a little bit unclear, but it's something to note. And so just this vast collection of data that's been sucked up into these models, you don't really know what they've been trained on. And so there's some liability there in terms of what data has been used and the potential to do things like generate code that has copyrighted material in it exists as well. I mentioned environmental impact earlier. These models are large, as we saw. They take a lot of electricity to run, these large GPU clusters. This is something that has started to get increasing attention. So the energy use of data centers, the amount of the world's energy consumption that's being devoted to running generative AI is starting to become non-trivial. So this, if you're interested in using these kinds of methods, or even if you're using ChatGPT casually, getting some understanding of what the environmental impact is of the use of this technology is something that you should probably want to do. The last thing I'll note here is privacy and security. So earlier this year, earlier last year, Elon Musk was asking people to upload their medical imagery into X for their Grok AI to have a look at. There are no protections on that, as people probably know. The industry here is unregulated with respect to health data. Of course, HIPAA still applies for anyone doing medical research or health systems. The basic models that we've been talking about, so ChatGPT and so on, they are not HIPAA compliant by default if you have API access. They are not storing user data that comes in a way that is compliant. Getting access to HIPAA compliant versions of these models is a little bit cumbersome, but there are ways to do it. So you can get access to OpenAI via Azure. There are other models you can access via AWS. So if you're looking at standing up some of these models in a way where you're actually going to feed user responses into them or user data into them, participant data from your studies, you need to be very careful in how you do that to make sure that you're actually compliant with applicable laws, right? So I think we ran up the time. I'll stop there. Maybe Vivek, you can let us know if we have time for a question or two before we finish out. Otherwise, I'm happy to follow up with people offline to address questions that may have come up.
Take a couple of questions, but thank you, Ben. Terrific. Covered so much of landscape.
Thanks.
Appreciate it. Any questions? Feel free. It's a lot to process, so they'll have to watch your webinar in slow motion.
Yeah, definitely.
Okay, we have a question.
Yep, just jump in.
Yeah, hi, thank you so much for that talk. I think it was, while this was the most simplistic explanation of machine learning and AI and LLMs that I've seen. So my question is around using LLMs for weak supervision. So, within the health domain, it's often hard to source labels from experts, and that becomes a bottleneck to, fine-tuning LLMs for specific tasks to improve performance. So where do you see a use case for using LLMs to generate labels in combination with, some kind of weak supervision where you do have examples from, limited examples from experts, and then the LLMs kind of scale that up?
Mm-hmm. Yeah, so just for benefit of the others on the call. So this notion of weak supervision, we talked about supervised learning. There's an assumption that the labels that you have are actually correct, or maybe that they're relatively low noise or relatively few labels that are incorrect relative to the size of your data set. But often the most expensive part of supervised learning is actually getting the labels. So in a health context, if you need a clinician to label something for you, that's going to be quite expensive. So this notion of weak labeling is just around, maybe we can find something where the labels aren't going to be perfectly correct. Maybe there's some non-negligible error rate, but maybe it's better to have more data with potentially incorrect labels or distance supervision. So maybe we don't have fine-grained labels, but we have coarse-grained labels. If we're trying to build customized models, maybe more traditional deep learning models, that is something that can be helpful. I think the only question there is assessing what the label quality seems to be, right? So you'd want to start by taking some of the data that you have where you'd like to get weak labels on it, run it through the model, get the suggested labels back, take it to a trusted source, get it assessed, and try to have some understanding of what the quality is, right? So mixing in data that's lower quality than the small amount of data you actually have is probably not going to be helpful. But if it looks like the model is able to reasonably solve that that labeling task for you, then those weak labels potentially have high value. So again, it's just a assessment problem to check and see whether that it looks like the weak labels are going to be useful for your task, and if they are, certainly using them is reasonable.
Thank you.
We'll take 2 questions. Will have to be tight because Jim has to run off to put out a fire. So Yin Cheng,
Okay.
you want to be brief? Yin Cheng, if not Ziping, why don't you go ahead?
All right, thanks.
Thanks.
Hi Ben. I just wanted to know should I go ahead or?
Yeah, please
go ahead. So we'll need to be brief.
Yeah. Okay. So in your talk, you have been focusing on general language model. I wonder whether there's foundation models that trained on large scale data set specifically for mobile health data, and how does that perform compared to models for general purpose?
Mm-hmm. Yeah, so the general notion of a foundation model is just a model trained in a similar way, generative pre-training kind of fashion, but not necessarily on text. So we didn't talk about other kinds of foundation models, but it's a good question. So there are some foundation models that folks are working on in the time series space. There have been a couple there. So in terms of mHealth signal processing from wearable data and things like that, those models are potentially useful at that level, right? So if you're interested in building maybe models that are able to leverage representations for different kinds of modalities, not just images or text, then foundation models from different areas are potentially relevant. And I think you would definitely expect that a foundation model, let's say trained specifically on waveform data, would be better than taking that data, trying to re-represent it as numbers, giving it to a language model as text, and then trying to reason over that text, right? So yes, definitely a role for other kinds of foundation models in the space.
We'll take one more quickly from Yin Chen. Are you ready?
Yeah, I'm sorry.
Okay,
Yeah,
good.
thanks for the wonderful introduction. I have a question. For example, if we want to use the large language model for mHealth diagnosis, for example. So when we want to transfer to the grants or proposals So what's the novelty side we should emphasize?
I'm not sure I caught the question. Can you just say the last part again? What is what we should emphasize?
Yeah,
the
yeah.
novelty we should emphasize.
I mean, well, if we did something and we want to apply for a grant, so I want to ask, what's the innovation side we should emphasize, because we just fine-tune the large language model. So is it are the contributes enough or not?
Yeah, that's a good question. So depending on where you're coming from and sort of where you're targeting your grant, right? So from the sort of NSF perspective, NSF is interested in fundamental advances in technology. It could be, so like the kinds of things they might be looking for, different, kinds of approaches to fine tuning, for example, as opposed to a proposal that's specifically proposing to fine tune a specific model for a specific task. Again, in specific programs like Smart and Connected Health, if there's a good rationale for doing that, maybe there isn't a model or you think you've got something that will perform better than the state of the art, that would be your innovation. I think on the NIH side, things are more wide open in terms of more application-oriented research. So they're definitely, building a fine-tuned model for a specific task where there are no models, or the current models perform poorly, or they're bespoke models, and you think you can do better using a foundation model or LLM type of approach. That would be your innovation, right? Your contribution is coming up with a new model, regardless of what its sort of its origin is. So yeah, I think you need to be a little bit strategic in terms of where you would pitch work, depending on what the level of contribution is. But definitely fine-tuning models for specific applications in the health space is a reasonable thing to do when you're looking at NIH-funded projects.
Okay, thank you.
Okay.
Thank